Alright, ladies and gentlemen, we made it to the final section of the basic sciences for the RTs. Is 1.3 fluid dynamics. Okay, so first up in this lecture is flow. So, moving right into it, hydrodynamics is the study of fluid in motion. This is going to be very important to what a respiratory therapist does during their daily practice, because you need to understand mainly how gases move, how they're going to react, how they're going to flow through a ventilator, and what changes you can expect, and how to address those changes. So first up that we're going to be talking about in here is flow. So this is the bulk movement of a substance through a space. And next we have pressure. Pressure is what is exerted by a liquid, and it depends on the nature of its flow. And then finally, this one, we have resistance, and this is for a given length of the tube. Flow resistance equals the pressure between 2 points divided by the flow. So mathematically, it's right there, resistance equals pressure 1 minus pressure 2 over, that's a V with a dot above it, which stands for flow in most of your respiratory textbooks, as you might see it as, I believe they use it as a cube sometimes. But, and of course you could rearrange this formula to determine your flow, and then that picture just shows you what happens. Your resistance can change based on a lot of things, vessel diameter, length, viscosity of the fluid going through. There's going to be a pressure gradient, which goes from a high pressure to a lower pressure. And that's going to be used to determine our resistance between those 2 points. So now we're going to move into some flow patterns. So there's 3 patterns of flow that go through tubes. We know them as being laminar, turbulent, or transitional. Okay, so in laminar flow, this is when fluid moves in discrete cylindrical layers or streamlines. And the difference in pressure required to produce a given flow through a smooth tube of fixed size is defined with School's law. So the delta P is the driving pressure, N is the viscosity of the fluid, L is the length of the tube, V is fluid flow, and R is the radius. Then we have an 8 here that's just for the constants. So this formula, when we have a fluid flowing in a laminar pattern, the driving pressure increases whenever the fluid viscosity, tube length, or flow increase. Also, the greater the pressure will be required to maintain a given flow if the radius of the tube decreases. So next up is turbulent flow. So some conditions cause flow to lose its regular streamlines. In a turbulent flow, the fluids move in irregular eddies and currents and chaotic patterns. We have a number that we include in this, and this is Reynolds number, which is NR. In this formula here, it's calculated. Don't really worry about knowing how to calculate it, just know that it's out there. So we have D is the fluid density, H is viscosity, V is linear velocity, R is the tube radius. We have our constants. So what happens to turbulent flow when this Reynolds number exceeds 2,000 in a smooth tube? The fluids can become turbulent. Then a turbulent flow, School's law no longer applies. So instead, the formula for driving pressures across the differences of the tube is now this. In this formula, F is now the friction factor based on the fluid density, viscosity, the tube wall, and roughness. L is the length, and then V is the fluid flow. And you can see here on this picture here, the bottom one is laminar flow. And you can see up here on the top is the turbulent flow. In the turbulent flow, you can see there's eddies that form. There's these little circles that kind of pop up here. Those aren't, not moving in streamlines anymore. They're kind of moving in a chaotic pattern. So finally in this is transitional flow, and this is a mixture of laminar and turbulent flows. So you have turbulent in the center of the pipe, and then you're going to have some laminar eddies form along the edges. Each of these flows behave in different manners because of their frictional properties and energy that's lost while they're flowing. They're going to have different equations that predict their behavior. This is the main type of flow that occurs during the respiratory tract. You have air coming through in a laminar pattern. Once it gets down into some of the smaller airways, it starts becoming turbulent, and that's where all your gas exchange. That's where the magic happens. It's down in that turbulent flow area. So in this one, the total driving pressure is the sum of the pressures from laminar and turbulent flow. You can calculate it again as delta P's are driving pressure, and it's just a combination of the turbulent flow up there, and then your transitional, or the laminar flow. Okay, and this is another exciting one for you. This is the Bernoulli Effect. This is again another scientist, Daniel Bernoulli, who discovered this one. So as velocity increases, lateral pressure, the force that's applied to the sides of the tube, is going to decrease. And this happens when you see a gas or fluid moving through a stricture or an obstruction. So its velocity increases and lateral pressure decreases. The magnitude of the pressure drop is proportional to the increase in the square of velocity. I know that's a mouthful, but just bear with me for another minute. Based on this law of continuity, the velocity of a fluid moving through a tube is constant. At a constant flow varies inversely with the available cross-sectional area. So what we have here is when, in the top picture you can see, it goes from a low viscosity to a high velocity to a high pressure going through a stricture or some type of obstruction. You're going to go to a low pressure, high velocity system. You can see there at the top how there's less coming out. It's moving kind of quicker, and then it returns back to its low velocity. And down here in this bottom picture, this is actually a way you can test this if you ever want to, impress your friends and be like, hey dude, come look at my Bernoulli effect. And if you put two cans kind of close together, they're empty, and then take a straw and you blow through the orifice between the two of the cans, eventually they're going to go together because the velocity between those in that empty space there becomes high and it pulls in, and it's kind of useful, and I'll show you in these next couple of slides. So next up we have is entrainment. So fluid flowing through a narrowing causes an increase in velocity. That's what we talked about with our Bernoulli, sometimes causing this pressure to fall below atmosphere. So if we create an opening at that point of the narrowing, you can actually pull other fluids into the fluids, being gas or liquid, into the primary stream. And this is where we have Venturi tubes that are specially designed entrainment devices that have a widening or a widening just after the jet or nozzle. So you actually can determine that a predetermined amount of air can entrain consistently, but you end up having a problem because you can develop a little bit of pressure, a back pressure of downstream from that entrainment port, and that can cause the amount of fluid or the amount of air or gas that is entrained into that little section there to decrease. And of course they already discovered this, so they came up with this Butot tube, which is a way to overcome the problem by restoring fluid velocity and lessening the downstream pressure. So it's more like I always think of it as kind of a pressure relief, so you don't get a buildup of back pressure. And the entrainment is when we end up working with your Venturi masks, where you have to deliver a precise amount of oxygen via a face mask, you can use your Venturi ports, and once you get to your clinicals or your labs, and you can open up a couple of these, play with it, you'll see that it has a dial on it, kind of like a sundial. But you turn the one, and it's either going to make the port bigger to entrain more air, more room air, or smaller to entrain less. And then, when the opening's smaller, the oxygen concentration that's getting to the patient is going to be a little bit higher. When that's bigger, there's more air getting pulled in from atmosphere, so the oxygen concentration is going to be a little bit lower. But it's just kind of interesting to understand when you're playing with that device, that's what's actually going on. That's that's the magic behind it. So finally, we have our fluidics, and this is a branch of engineering that applies hydrodynamics principles to the flow of circuits like pressures and flow sensing. So first we have the Coanda Effect, and this is observable when a fluid flows through a small orifice with properly contoured downward streams. So this is a phenomenon that happens when a jet of flow attaches itself to a surface and remains attached even though the surface curves away from the initial jet stream. So in a free surrounding, the jet of fluids entrains and mixes with the surroundings as it flows from the nozzle. So see here is a hairdryer, and it's blowing a stream of air across a curved surface. So what happens is the gas that is moving connects to that curvature, and it kind of pulls it from its mainstream, and you can see it opens up like it would open up a little bit, but now it's following the path of the curve around that object. So that's moving along, and that's all I have for the basic sciences. But we'll be back. I'll come up with a couple more videos and some other topics that might be interesting for everybody out there. Thanks for listening.